Hello guys, in this video we'll learn about vector search with LLMs and Qdrant DB using Rust. Before we start, let's talk about why do we even need vector databases. Now traditional databases work well for structured data like numbers, names, categories, but when dealing with unstructured data such as raw text, images, audios, videos, traditional databases struggle to perform efficient search. For that reason, we need vector databases. And why do we need vector search? Now, vector search or nearest neighbor search helps find similar items by measuring the distance between their embeddings. Instead of exact keyword matches, it finds semantically similar result. For example, you want to search how to cook pasta, should return result like best spaghetti recipes, even though the keywords don't exactly match, but you get some result instead of no result. Now similarly, image search find similar looking images based on pixels embeddings, speech recognition, match spoken words to stored voice examples. So for all those reasons, we need vector search. And there are tons of vector DBs available on the internet because this wave of LLM has given a rise to vector database and its usage. There is Qdrant DB, there is PG Vector. For this video, we'll be using Qdrant DB, but in a future video, we'll also look at PG Vector and different other vector DBs. Now these DBs are optimized for storing and searching high dimensional vector embeddings efficiently, unlike the traditional databases. They could handle, like millions and billions of embeddings, used fast indexing and stored metadata to filter results. For example, like, search for documents from a specific author. Most common use case for such vector DBs is LLM chatbots, search engines, recommendation systems, fraud detection, image and video search. So these are like few of the examples of where vector DBs can be used. But in this video, we'll design a system where we'll store some data and then try to query it and see how vector DBs work, how embeddings work with the models from LLMs. Vector DBs also help you save your cost. So consider it as every query that you receive, you go to the LLM to process it and get the response. Now every query you send to the LLM, you are consuming your tokens, and in terms it's costing you. What you could do is you know your use case, so you can get the embeddings from your LLMs. There is models that provide embeddings, which we'll see in a minute, and then you can store in your vector DB, and then every query you get, you just drive the vector for it, the embeddings, and then from the DB you can search using that, which is exactly what we'll do in this video and understand how could it efficiently help us reduce our LLM usage cost. So without further ado, I think enough of the talkings, and by now you should have understand what we are trying to achieve from this video. If you do, there is tons more left in this video, so make sure you stick around, watch till the end. And as we start, there is a link to my Discord in description. We are building a community of like-minded people, so make sure you join it. For this video, we'll be using Llama 3.21b for embeddings. Now there are different models available on the internet that provide you embedding, be it open source or paid models by OpenAI, Gemini, but we'll be using like open source models since they are accessible to everyone watching this video. So but the concept remains the same. So we don't have any model running right now, and we have Llama 3.2 on our machine, so we'll just do Ollama run Llama 3.21b. So let's take an example. How can you retrieve the embeddings? So we'll just curl on our local host since the model is up and running, and we'll use /API embed. Now OpenAI provides its own API, which is API/embeddings, but Llama provides API/embed. So we'll be using this API with Llama 3.21b, and we want embeddings for why is the sky blue. And there you get, this is basically not human understandable. I would say it's human readable, but not understandable because it's like lots of it's basically a vector. So as you can see here, so let's not go in the details right now. We'll understand more through when we code. So we have our model now up and running on our machine. So we'll be using Qdrant DB for this video, and Qdrant DB is probably one of the topmost vector search DB going around as we speak. So it's used for a lot of use cases. It's open source and provides you SDK for Python, Go, Rust. So as you can see, quite good reviews and has integration with probably all the models that we have. We can just run locally with Docker, run and expose it on the port, which is something that we'll do in a minute. We can, perform advanced search, RAG, we can do data analysis and anomaly detection, AI agents. So we'll cover all of these use cases, trust me, one by one on this channel. So make sure you are subscribed and stay tuned on the channel. Now, if we move to Git, as you can see, it's very popular, and we get SDKs as well that we can check here. So like Go client, Rust client, so we'll be using Rust client. And as you can see right here, you can read here about vector search and all those stuff that vector DB as Qdrant provides. So we'll be using Rust client, and right from here we'll use this command to spin up on our machine. So make sure you also expose the gRPC port. So back to our terminal, and we'll just do docker run, and let's add -d as well, so for detached, and we have our container up and running. There you go, we have our Qdrant DB up and running. Now let's add a few dependencies that we need, and then we'll start diving into the code. So let's quickly add our dependencies, and I'll do so by adding all in one go. We need Tokyo, request, Saturday, JSON, and Qdrant client. So we have our dependencies add, and right here, as you guys can see, we have Qdrant client, request, Saturday, JSON, and Tokyo. Now once we have our dependencies, let's move to manrs, and here we'll start adding our structs, and then along the way we'll also discuss everything. So first of all, let's add a few structs that we'll need to insert our documents to DB and also to retrieve our response from embedding endpoint. So struct document and ID as U64 and text as string. On top we need to derive, debug, serialize and deserialize. Then we need Ollama embedding response. So struct Ollama embedding response, and that would be embeddings as whack of F32, and we will derive, debug and deserialize, and then couple of const. One is Ollama API URL, so we'll be using localhost since we already run the model, localhost and 11434, and then another host we need is Ollama model, and we'll be using Llama 3.21b depending on which model you are using, just provide it here. And now let's connect to Qdrant DB. So main result as unit or Qdrant error, and Tokyo main, and here we'll provide our Qdrant client config. So let's name this qconfig and Qdrant config. So URI as HTTP localhost 634, and let's wrap it in the string. Once we have this, Another thing that we need is timeout. So let's say duration from seconds. Let's use the duration from seconds. Let's say 10 seconds. Next we need is connect timeout as again duration from seconds as 10 seconds. And next we need is keep alive while idle as false. API key, since we are connecting locally, we don't need any API key, but if you are connecting to Quadrant client, Quadrant cloud or some cloud variant of, or some restricted variant, you need API key. And compression as none. And check compatibility, make sure to set it as false because by default it's true, and on local we should set it to false. And that's for our config. Now to connect to our client, we'll just do let Quadrant client is equals to Quadrant, and let's get Quadrant new and pass your qconfig, and we get the client. Now once we have our Quadrant client, first of all we'll need to create a collection. So let create collection, and we'll be using create collection builder. There you go, new. And here we have to provide our name for collection. So let's say I name this collection as documents, and then we have to provide vector config. So here we'll be using vector params builder new. And now here we have to provide the size. Now this size depend on the model which model you are using, and you can simply Google to find the embedding size. As you can see, for Llama 3.2 it is 2048. For different models it's different, so make sure you are using the accurate. So here we'll be using 2048, and then different distance that you can use, and try to experiment with different distance here on what changes. As you can see, unknown, cosine, include, and dot or marathon. So I'll be using cosine. And then we have quantization config, and we'll just use is scalar quantization builder, and just use it default. Now why do we need quantization config, and why do we used scalar quantization config? Now instead of storing vector as a full precision floating point numbers as F32, F64 that we just saw in the embedding endpoint response, Quadrant compresses them into lower precision types, reducing memory usage as well as speeding up the search. And when using scalar quantization, like when using this specific method, vector component is stored in a lower bit format, for example 8-bit integers instead of 30-bit 2-bit float points. Now what that does is it significantly reduces the memory footprints while still allowing the efficient vector search. And when should we use it? Like if we are working with large scale vector databases and want to optimize for memory and speed, we should use scalar quantization. So I hope that's clear, and if that is, we'll be using different techniques in videos going forward, so make sure you are tuned. And once we have our create collection, we'll just do Quadrant client, which is the client that we just add, Quadrant client dot create collection, and we pass our create collection. So let's await, and then we get collection added. Now if we run this code, we should be able to successfully create our collection, but that's not it. We want to add some data, generate embeddings, and perform search as well. So for that we need some data, and that is we can add some vector of documents here. So I just generated a bit of data and added here, as you can see, doc1 to all the way doc7, where we talk about different programming language: Rust, Python, JavaScript, Go, Kotlin, Swift. So you can just generate it, or I'll drop down in the description so you guys can copy same data. It's pretty less, but enough for us to learn the concept. So we have our data now, and now we need to generate the embeddings. And to do that, we will be making call to our API. So let's get rid of this error. And now let's add async fn generate embedding for text. And here we pass our text and we get vector of f32. And let client will be using a request. We can also use Ollama client, but for this video we are just using the request client. And response is equals to client dot post, and we pass our const, which is the URL. So that is Ollama API URL, and then we need to pass our JSON. So we'll just pass using Serde JSON, JSON, and right here we'll add model as Ollama model and input as whatever is our text. So instead of calling /generate /chat completions, we are just calling embeddings. That will return us the embeddings await dot expect failed to generate embeddings. And once we have the response, we can also use dbg to check the status. So response dot status, and let embedding let's call it data Ollama response is equals to response dot json dot await dot accept failed to parse response maybe. And once we have our embedding data, which is vector of vector, but if you clearly note in curl, we just need the inner first vector because we will be sending just one input. So embedding data dot embeddings dot first dot cloned dot expect no embedding found, and we should be able to get embeddings from here. Now once we have our single text embedding generation, we need to iterate over our document. So right here we'll just do async fn generate embeddings text and str, and return vector of f32, and let mutable embeddings vector with capacity, and we'll just use the same capacity as text.length for text and text. Let embedding is equals to generate embedding for text. We pass our text, we'll await for the response. Once we get the response, we'll just do is embeddings dot push. So let's use our embeddings dot push embedding, and once we get our embeddings all, we'll just return the response. So let's write. Okay, so we have our, let's convert it into text. Okay, so we have our generate embeddings, which is iterating over all the text, and which is basically these texts. So now we have our call to our endpoint as well. Now let's continue right here where we upsert our embeddings by generating. Now let's generate the embeddings and use them. So embeddings generate embeddings, and here we can pass the text. So and our documents dot iter dot map, and per document text as str, and collect as vector. So this ensures that we pass and generate the embeddings, and then let's await for the response. And once we have our embeddings, we'll just go ahead and convert these documents and their embeddings into the quadrant points to store. So let's do that. Let points vector of point struct and documents dot into iter dot enumerate dot map, and here I doc, and we will create a payload that also comes from quadrant. So basically this is to store our payload. You can just do JSON and ID as doc ID, and then another thing that we have is text, which is doc text and try into not unwrap. So we get our payload, and now let's construct the point. So we'll just do is point struct new, and here we'll just do point ID from, let's use point ID from, and pass doc ID, and then our vectors or embeddings, we'll just do embeddings of our I dot clone, and the final thing that we have is payload, which comes from here. So that is basically just storing our embeddings, and once we have it, we'll just collect and then we'll just upsert it. So quadrant client dot upsert points, and here we'll again use upsert builder now. So upsert points builder new, and collection name, which is the same, documents, and the points, and then obviously we have to await for this to complete. So let's go over what we have so far. Is we create our collection, and then we insert some data. First of all, we want to check the embeddings for them. So we call our Ollama API to get embeddings, and then once we have our embeddings, and here we need, okay, so once we have our embeddings, we create point structs to insert our points. So basically how we insert the point is, for this document we have, or the collection, we have document ID, then the embeddings that we get from Llama, and then the payload. In payload we want to insert the text. So when the similarity matches, we want to ensure that we are using the text that we want. So let's say I search what is Rust, and it gives me this result. Rust is a systems programming language, or how cool is Rust, it should give me this as a similarity from the data. So now let's try to run this, and before we search, we want to ensure that we can insert the data properly. So just head to the terminal, and here we want to ensure our model is up and running. It's not, so run llama 3.21b, and once it's running, we'll just do is cargo run quite. So right now, if we are able to successfully get out of the program, meaning we are able to run this. Actually, we just missed one thing. So here we have to provide the complete path. So let's say /API/embed, and now we write out, and now let's do run. So we just do cargo run again. So we get document already access, which means because we are running this code again and we were first time successfully able to create document, and because we'll be running this code again and again, so let's do a delete document before we create every time. So here we do is delete document, and we'll use delete collection builder, and new, here we'll pass the collection name. So name is documents, and await. So let's try this now, and right here we do print successfully created collection, and inserted our points. You can also list collection, but since we will be working more on search today, so let's not. Okay, so as you can see, cargo run, it first prints all the dbg that we have, which is all the 7 times our documents get their embeddings, and then finally we are able to successfully save it. So meaning our code works perfectly fine till now, and now the next thing we have to do is perform search. So to search, we need first of all a customer query. Let's clean this. Okay, first of all we need a customer query. So for that you can take the input or you can hard code it here. So let's say tell me about Rust programming language. That's the customer query. Okay, and then we want query embedding, generate embedding for text directly, and we pass query text. So we get the embedding for query, and once we get the embedding, we'll do search. So let's search result is equals to quadrant client and search points, and here we'll use the builder. So search points builder, and new, here we pass documents and query embedding, and then the limit of how many matches we want. So let's say we are just looking for a single match, because this will display all the matches on basis of similarity score. So once we have it, we just need is inside actually with payload. Yes, we need payload, so with payload as true, and then we can await here, and then we can just go ahead and print our search result, and search result we can print whatever we want, but I will just look to print everything, and let's print formatted. Okay, so that's pretty much all that we need here, right? Okay, so what we are doing here is we are creating collection, we are upsetting our similar points or data, and then we are querying on basis of that. So let's go ahead and test it. So what we'll do is cargo run and quite. Okay, so what we get here is, let's see, first of all our collection is created, the data is inserted, and then we get our search result, which is when we query, our query is tell me more about Rust, as you can see right here, and the result that we get is Rust is a systems programming language that is memory efficient and reliable. Okay, and we see the similarity score is this, and let's say if we try to search for something else, so let's say we try to search for let's say right here, instead of Rust, tell me about JavaScript, let's see, and we try to run this. Okay, JavaScript is a versatile language commonly used for building interactive web applications. Now see, what is the benefit of using a vector DB is, let's say you are not using, so as you can see, we are not using a LLMs, slash generate or slash chat completion endpoint. We are just using embeddings. We are generating the embeddings for our text, which is only once. Yes, we have designed this program that every time we run, the collection will be created, but data will be inserted. But you can just insert it once, and then all you get is customer query, generate the embeddings, and then search in your own DB for a similar response to that. This could be very useful for recommendation systems and everything where you want all the data and everything at your end. So let me know, what do you guys think about this? I'll catch you guys in another video with another interesting topic. Until then, bye bye.